Hello and welcome you all to another video. Have you ever wondered, you know, uh, you would have seen this thing at a lot of places. Consider this series, 1/1, that's all, 1/2, that's 1/3, and something going to infinity. So if you know stuff about this is obviously a harmonic progression, and if you know about the basic harmonic progressions, you know that this thing is divergent, contrary to what some people might tell you, right? But this thing is divergent, so this series goes to infinity, right? But obviously it has a very it has some very deep connection with the Riemann zeta function as well, because this is zeta for 1, but we will not get into that. What we do want to get into is consider this thing only. So this series can be written as the summation from what, I equal to 1 to infinity of 1 over x, right? And if I were to just integrate this thing out, just in a crude way, let's say from if I were to just turn this summation into an integral and integrate asymptotically, you see that this thing will approach ln or some n to some for some n value, because this will not go to infinity. We will not let it go to infinity, rather we'll take the limit of n as n takes to infinity of the summation I to 1 to infinity. This should be x to 1, sorry for that, and to 1. Alright, so this will tend to ln of n. Right. Now the question is, what will this limit tend to? So limit of n tending to infinity of the summation of I, this time it's I, summation of I from 1 to n of 1 over x minus ln of n. Firstly, will this thing even tend to some number? Because this obviously is this is known to be an infinity, that should be an infinity. So in a way we have infinity minus infinity, and this is something which you obviously cannot determine. But it turns out this thing tends to one value, some value, and this value is known as gamma, or at least I'm going to call it as gamma over here, gamma, and this gamma is known as the Euler Mascheroni constant. So it was firstly determined by Leonhard Euler. That's not a surprise, obviously. Then it was more accurately and stuff like that. It was more accurately determined by Lorenzo Mascheroni, who was an Italian mathematician. Hence the name Euler Mascheroni constant. So this is a very peculiar value. It is 0.5 to something. And if you want to know more about it, number 5 has this great video, which I'll leave a link to down in the description. So if you want to check about it, you can. Okay. So what we want to actually see in this video is the relation of this constant with the factorial, with the factorial, which is n factorial, which is like n times n minus 1, n minus 2, to 1, obviously. So on the first side, you might think, is there any kind of relation between these two distinct mathematical quantities? And it turns out that there is a pretty significant relation, because you can write the value of the factorial in terms of the Euler Mascheroni constant. Let's see how. Okay, so before that, you'll have to we'll have to take a brief review. And in my very first video on this channel, I derived the gamma recurrence relation. So the gamma function is a very significant function. Again, Euler's gamma function. Euler is everywhere, you know. So the gamma function for some z, I'm going to call it z because you know you call it primarily z. You know, when you are talking about the gamma function of complex numbers, and the kind of stuff that I'm going to talk about in this video is primarily related to the analytic continuation of the gamma function. So you know, analytic continuation in very simple terms is basically, you know, like let's say there is some function which is, you know, kind of, you know, continuous, if you want to call it, in some discrete set, and now you want to increase that, you know, the span of that set. So you take some other function which is, you know, continuous in some other set, and and it turns out that those two functions are continuous in some overlap. So there is some union of those, you know, of those sets where both of those functions obviously have the same values point to point. So then you say that both of those functions are the analytic continuations of each other in those discrete sets or regions. So it's, you know, so that is a very, you know, kind of like, you know, so analytic when they are in the complex thing. That's the thing, and that is a very simple definition of, you know, not a definition, but like, you know, more of an intuition for analytic continuation. But we are again not going to get into that. So, you know, gamma of z is defined by this integral 0 to infinity of x to the minus z e to the minus x dx, right? And you know, you can get from this integral to a product kind of thing. So you can get to this thing over here, that actually you can change this whole integral into a limit which tends to infinity. So limit of n tending to infinity of n to the z times the product from I to n of I plus z. So it turns out that this thing can be converted into this thing, and this thing is known as the Gauss representation of the gamma function. Again, you know, one of the gods of mathematics, Gauss representation gamma function. And you know, just for like, you know, how to get from this to this, well, it starts off by, you know, seeing the limit form of e to the minus x, which is 1 minus x over n. Actually, I should not write it out in this fashion. Limit of n tending to infinity of 1 minus x to the n over n. And this is, you know, this is a very famous limit, and when you substitute this thing over here and just do some, you know, integration by parts again and again, you end up with this thing over here. That's how you get from this to this. So that's that. We are going to start by taking this, you know, as a postulate, and you know, going then doing some minor tweaks in this thing and seeing where we end up. So let's get cracking. Firstly, what you know, let's just divide, you know, the upper and the lower, sides of this fraction, the denominator and denominator, by I. So we will have gamma of z in the limit of into infinity of n to the z times pi I from pi to pi equal 1 to n of, you know, 1 over z by I. First, we have divided both the numerator and denominator by I. right? And this thing can be written as the limit of n tending to infinity of n to the z pi I 1 n 1 plus z over I inverse. Obviously, right, you can write it out in that fashion. Okay. Now let's notice that n to the z can be written as e to the z times ln n, right? For from the basic properties of natural log and exponentials, and just keeping this side as it is. Right. And now I can do one thing, which is add 0 in this, and it will be clear in a moment as to why I'm doing that. So I can write 0 as the sum of I from 1 to n of sum z over I minus I equal to 1 n of z over I, right? That is still a 0. And now I will put this representation of the 0 over here. So we'll just keep this thing on one side and see what is going to happen on this on this exponential over here. So then we'll have a z and an n plus the summation from I to n. Still we have the limits over here. So n is still going to infinity. So a z over I minus I equal to 1 n z over I, right? So now what I'm going to do is z is not going anywhere. Z is what it is. Z is some variable, but it is not some part of the summation. So it will not change its value at every step of the summation. So we can take this out at our will. So now I can write out that this thing over here is summation of I 1 to n of z over I minus of the summation of I from 1 to n of z over I minus ln of n times z. Now why did I do that? And what is this thing over here? Well, obviously, firstly, z should not be here, 1 over I. And now it starts to make sense. What is this over here? Because as n goes to infinity, this summation basically becomes 1 plus 1 over 2 plus 1 over 3 plus 1 over 4 and all the way up to infinity. And this thing is ln of n. N is still going to infinity. And this thing over here is the Euler Mascheroni constant. This is gamma. And hence we can write this thing over here as being the summation from I to 1, from I to n of z over I minus z times gamma, right? Now I'm going to substitute whatever I have over here in place of e to the that thing, because basically this was the power of the exponential over here. So let's just quickly do that and see what we are going to end up with. So again we take this thing over here. So we have limit of n tending to infinity of e to the summation z over I from I to n times e to the minus gamma, because obviously I can take the exponentials out from the properties of exponents, and this gamma z times pi I to n of 1 over z by I whole inverse. And now this summation over here, this thing over here is basically multiplications of e to the z over 1 times e to the z over 2 times e to the z over 3. So this So this whole thing over here can be taken inside this pi, right? Because this goes like a product. So now we have limit of n tending to infinity. So this thing over here can be written as limit of n tending to infinity of e to the minus gamma z times the infinite product I from 1 to n of z over I times 1 over z over I to the minus 1, and this thing over here is equal to the gamma function. This is known as the Weierstrass representation of the gamma function. And you see that the gamma function over here is represented in terms of the Euler Mascheroni constant. And remember that gamma of any z is equal to z minus 1 factorial. So hence the factorial is related to that crazy limit value which is the Euler Mascheroni constant. And in this way, two seemingly very distinct quantities in mathematics are related in such a beautiful way. The Euler Mascheroni constant shows up at a lot of places in string theory, I am told, and again the number 5 video is a great resource for knowing where it shows up in physics, and also the Wikipedia page is a good thing, and the gamma function is literally everywhere in physics. One thing to tell you is Gabriel Veneziano, who was the first guy who started the string theory trend, actually stumbled upon something known as the beta function, Euler's beta function, which is represented in terms of the gamma function, and he found out that the amplitudes of all those strings can be represented in terms of the beta function, but we'll not get into that. But that is just to tell you that gamma function is everywhere. One more place where it is in the field of fractional differential equations, because you can define gamma function for not only integer values but for fractional values as well, and that does tell you that you can also define it for you can also define fractional factorials as well. That is true, and fractional differential equations are quickly picking up pace in the field of physics, and a lot of people are building upon fractals and chaos and stuff like that in different fields of physics. So both of these things are very prevalent in physics, and that is just one crazy, elegant, beautiful, whatever you want to call it, way in which these two things are related. So I hope you learned something new today, and if you like what you learned, please give this video a like, share, subscribe, comment, whatever, and see you next time.